of the different refractory materials, and that'll take us through today, Monday, Tuesday, and Wednesday, 4 days of different materials. So today is silica refractories, SiO2-based refractories. Second part of today's is alumina silica. So we'll use a combination of alumina and Al2O3 and silica 2. So each one of these materials, we'll look at what the raw materials are, the phase relationships, the phase diagrams, how the material is processed. We'll examine the microstructure, and then look at some of the key properties of each material. So the raw material for we're still admitting people here. Okay, I think everybody's here. The raw material for a silica refractory is quartzite. It's just an SiO2 mineral. And this is the chemistry for quartzite. About 98.6% SiO2, and then the various impurities in small concentrations. Al2O3, alumina. There's an iron oxide, Fe2O3, calcium, CaO, magnesium, MgO, and some alkali, Na2O and K2O. So they classify this type of refractory as a conventional refractory if it's 0.5 to 1% impurities. If it's a more pure material, a super duty silica, it's 0.2 to 0.5% impurities. So that's the raw material. When you apply heat to this material, the silica SiO2 exhibits polymorphic phase transformations. And there's two types of transformations in this material. One is called a displacive transformation, and that's a very rapid transformation. You're simply distorting the crystal structure. You're not breaking bonds or reforming bonds. You're just distorting the structure into bond angles and distances. And that's a very rapid displacive transformation. And then there's another one, reconstructive transformation. Here you alter the crystal structure. You're actually breaking bonds and forming a new crystal structure. And that's a very slow or sluggish reaction. So why are these important? Well, whether it's a displacive transformation or a reconstructive transformation change. Some of these volume changes are significant, and the volume change can disrupt or destroy the actual refractory structure. So we have to work around these transformations and know the extent of the transformation and where they occur. Pure silica, pure SiO2 melts at 1723 degrees C. So it has a fairly high melting point. This is a diagram showing a displacive and a reconstructive phase transformation. So we start at the top. We have some type of crystal structure, and that's A, and then we can go to B or C, those diagrams. And we have distorted structures. The bond angles have changed, maybe the bond lengths have changed. That's a displacive transformation. Figure D is a reconstructive transformation. You can see these structural units, which are represented by a square with atoms at the corner and a different atom in the center, have now, the bonds have been disrupted and we have a new crystalline structure. So displacive transformations are very rapid. When you hit the temperature where they transform, it's very rapid. Reconstructive transformations take a long time. So in the silica refractory, These are the different transformations that take place. There are three crystalline structures. There's quartz, tridymite, and cristobalite. Quartz goes from low quartz to high quartz. That's a displacive transformation, and that happens at 573 degrees C. And there's a 0.9% volume expansion that takes place with that transformation. Tridymite goes from low tridymite to middle tridymite to high tridymite. So there are two displacive transformations, one at 105 degrees C and one at 160 degrees C. So going from low to high tridymite is 0.4% volume. Quartz is a low temperature form. Tridymite and cristobalite are the high temperature form. So quartz is the raw material. To use quartz as a refractory, you convert it to tridymite or cristobalite. And there's a transformation, again, a displacive transformation for cristobalite going from low to high, and that takes place in this temperature range, 200 to 270 degrees C, has a bigger volume expansion, 2.8%. So when you make a refractory from quartzite, you start out with quartz. You want to transform it to either tridymite, high tridymite, or high cristobalite. Both of those are reconstructive transformations. (867 degrees C) is based on a thermodynamic calculation. Theory, high quartz should go to high tridymite at this temperature, but the kinetics aren't there, so it doesn't really happen. And then this reconstructive transformation from high quartz to high cristobalite takes place at 1470 degrees C. And essentially, this one takes place in the same area, really about 1500 degrees C or higher. So in high quartz, the transformation to high cristobalite, there's a 14.3% volume increase. And when you go from high quartz to high cristobalite, there's a 17.2% volume increase. So ideally, when you silica refractory, you want to start out with quartz, you want to transform it to high tridymite. You eliminate this volume change, you now have a stable material, and then this displacive trans 0.4% is lower than this other one, 2.8%. But in reality, you get both high tridymite and high cristobalite. Quartz, you're going to end up with a combination of tridymite and high cristobalite. You've gone through these reconstructive changes, so you don't have to worry about these large volume changes, but you still have the displacive volume expansions. So this summarizes the phases and dimensional changes with the crystal structures in silica. The beta 1 to beta 2 tridymite, there were two displacive transformations taking place in this temperature range from about 117 to 160 degrees C. Overall, the linear change was plus 0.17. We described the volume change of about 0.5%. This temperature range around 200 degrees C goes from alpha to beta cristobalite. The linear change is about 1%, and the volume change is 2.8%. At 573 is the alpha to beta quartz transformation. The linear change is about 0.26, maybe 0.45%, and the volume change is around 1% or a little higher. And then transformations, beta quartz to beta tridymite, the reconstructive, and beta quartz to beta cristobalite, the much bigger change, so 5.5% less the first one, 6.6% for the second one. Linear changes, And then our larger volume changes, 14.4 and 17.4. You can go from the tritomite to cristobalite, linear change. That's a reconstructive transformation of about percent. And then when you melt these materials, beta tritomite melts at 70 and beta cristobalite at 1713. There's a volume change when it melts and a linear change. Not all of these are shown here. So those are all the possible transformations, their linear changes, and their volume changes. This table just summarizes some of the crystals. So for alpha quartz, the crystal system is trigonal, and then you have the lattice constants and the density. So alpha quartz is 2.65, that's grams per cc, specific gravity. Beta quartz is hexagonal, 0.49. So when you go from alpha to beta quartz, there's a density change. It's a lower density crystal structure. So there's an increase in the volume. That's the reason for the displacive transformation volume increase. Alpha cristobalite is tetragonal. Its density is even lower, 2.33. Beta cristobalite is cubic, it's 2.21. And other forms of tritomite, alpha tritomite is 2.26. It's rhombic. Beta 1 tritomite is hexagonal. Beta 2 tritomite is hexagonal. And its density is 2.27. This one's about the same. It's not given. But what happens when you go from a quartz to a reconstructive transformation to either cristobalite or tritomite, you can see the density is much lower, so the volume is much bigger, and those big changes in density and volume are what we were just talking about with the big volume increases. There's a couple other forms of silica not seen in our materials, in refracting materials. There's some special high pressure forms of silica. So I just mentioned the different crystal structures, and so I showed this slide, I think the first day, but I'll show it again. There's a cubic structure, and the atoms are normally located at the corners. If it's body centered, there's an additional atom in the center. There's an additional atom on the face of the tetragonal. And you can also have tetragonal body centered. The rhombic, you can have atoms on one face, while opposite faces, body centered, or all the faces, monoclinic, centered on opposites, triclinic, and two forms of the hexagonal structure. So all of these crystal systems have an axis and a y length on the unit cell. That would be A, B, or C, corresponding to those three directions. And they have angles between the different axes, alpha, gamma, and beta. So a table that just summarizes for the different crystal, the diagram for, if we start out with cubic, the simple, so the three lengths are the same, it's a cube, and the three angles are the same, they're all 90 degrees. Alpha equals beta equals gamma, they're all 90 degrees, it's just a cube, and you only have to specify one length. If we look at another one like tetragonal, A equals B, but now the axis in the C direction is longer, and all three angles are the same also, 90 degrees. So you have to specify A and C, the two lengths. And on the other extreme is triclinic. None of the three lengths are the same, and none of the three angles are the same. So you need to specify all three lengths and all three angles. So this table just summarizes the different crystal structures, the, the length of each side in a unit cell on that crystal, and the bond angles. So we have our quartz material, SiO2. We apply heat. We would like to end up with tridymite. It's desired because it has the smallest displacive volume transformation. That was point. So if you have a silica refractory, you convert the quartz to tridymite, and then you use it in an application, you heat it up, cool it down. You want the smallest volume change that disrupts the structure the least. You want it all in tridymite or cristobalite because you want to avoid those reconstructive transformations. You don't want any quartz left in the structure. So a well-made silica refractory does not contain quartz anymore if it's heat treated properly. So you've avoided these large reconstructive phase transformations of 14.3 and 17.2%. Of course, the tridymite and cristobalite is a sluggish reconstructive transformation. So the heat treatment takes place over a long time to make that conversion to tridymite and cristobalite. So since it is a slow reaction, even at elevated temperatures, you can add lime, a lime mineralizer, CaO. So the mineralizer helps this transformation to take place at a more rapid pace. So add the mineralizer to transform quartz to tridymite and cristobalite. So you add about 2%. That forms a small amount of liquid phase. The quartz dissolves in that liquid phase, and then you recrystallize tridymite liquid phase. So silica refractories have 2 or 3% CaO addition to cristobalite or tridymite. So you have to control the transformation rates and the volume changes. And again, this just summarizes a 3 quartz is 2.65, and you're going to a lower density tridymite or cristobalite. And that's where your volume changes occur. For the phase relationship, CO2 and CaO. So if you have 97% silica, 3% lime. We just mentioned it promotes the conversion of quartz to cristobalite. So at this combination, as you add lime, you create more liquid. So 3% lime addition to silica at this temperature, 1436 degrees C, you now have 8% liquid phase in the refractory. If you increase the temperature to 1705 degrees C, phase goes up to 11%. So the rule here is that when your refractory contains 30% liquid phase, it's no longer volume stable, and it will go through a deformation or creep very rapidly. So this is the phase diagram for silica and CaO. It's a binary phase diagram. And this side of the diagram is 100% SiO2, and going in this direction from left to right, you go up to 100% CaO. So 3% addition of lime, you're right on the, just to the right of the 100% SiO2 axis here. So as you go up in temperature, you're going through aconite, tridymite, and balastanite. Balastanite is just a calcium silicate. Here you have tritamide and the wollastonite again. And then when you hit 1436, right here, you now have this two-phase liquid. So you're forming liquid right here, and you can use the lever rule to figure out the percent. And I think I mentioned it was 8% over here. And then when you hit 1470 degrees C, you now have cristobalite in liquid. And then as you get up here to 1705 degrees C, above that point, you'll have complete liquid. And this is a two-phase liquid field, two immiscible liquids. So you form your first liquid at 1436 with tritamide in liquid. At 1470, you then have cristobalite in liquid. And then finally at 1705, you have complete liquid. So you can use phase diagrams to see what's happening when you make a so you addition of lime, you can see exactly what's going to happen. Obviously, if you add a lot of lime, you start running into all these other compounds and low melting eutectics and so on. So there's other phase relationships we can look at: SiO2 and Al2O3, SiO2 and TiO2. Impurities for this system cause a rapid drop in the melting point of silica. So 95% SiO2 and only 5% Al2O3, you have a 100% liquid phase when you reach the temperature 1590. A 90% SiO2 and 10% TiO2, you'll again have 100% when you raise the temperature to 1553 degrees C. So obviously you've lost volume stability, which is 30% maximum. So this is a summary of different impurities, basically a phase diagram summary. This is the percent impurity from 0 to about 14, and this is the temperature. And we just mentioned SiO2 and Al2O3 for O3. And now it's in degrees Fahrenheit, but you can see here, percent Al2O3 produces this eutectic at 2903. So it's really lowers the melting temperature. SiO2, TiO2, we just looked at. Here's the line for TiO2, and there's a eutectic at 2822 degrees. You can see how either alumina or titania lower the melting range of are also some alkali impurities, Na2O and K2O, and they're really lowering the melting point. It's off the scale of this chart, but if you have of 31% K2O potassium oxide, the melting point drops to 1385 degrees F, and if you have 26% Na2O, melting point drops to 1460 degree F. So impurities have a big effect in silica refractories on lowering their use temperature. And if you look at all these different types of impurities, TiO2, Al2O3, Na2O, and K2O, if you have a 98.8% silica refractory, and the sum of these different impurities is in the order of 1.2%, and they are fluxes. So these are the fluxes or the impurities. You'll have 30% liquid at 1650 degrees C. Well, that's in the area of steel-making temperatures. So that's very undesirable to have that impurity level in a. If you're at 99.6% silica and the fluxes, the combination of these fluxes is 0.4%, you'll only have 10% liquid at 1650 degrees C. So as soon as you reach 30% volume of liquid, you're unstable. The ASTM standard that specifies silica refractories has another definition. They call it the silica flux factor. That equals the percent Al2O3 plus 2 times the total. So the alkali content would be Na2O and K2O. And if the silica flux factor is greater than 0.5%, it's a conventional silica refractory. If it's less than 0.5%, it's a super duty or higher performance refractory. So we can plot the amount of liquid that forms as a function of temperature. And we can do that at the two different flux levels I just showed, 0.4% and 1.2%. And let's 4%. So this goes along rather, it's a rather flat slope. And all of a sudden, when you get about 1650 degrees C, degree C is up here, degrees F is down here, you have a very rapid increase in the amount of liquid content, all the way up to 100%. The higher flux content, 1.2, you're going along fairly stable. And then somewhere in this region, maybe 1550 degrees, 1600 degrees C, you really have a rapid increase in the amount of liquid that's there. So silica refractories hold they're creep resistant, they have good hot load up to this, but as soon as you exceed them, you have a very rapid increase in the liquid content. When you process this material, you start out with quartz, and all of these pressing operations are pretty similar for most refractories. You have to crush it to a finer size. You screen out different sizes. So you use a particle packing theory approach to recombine the different sizes to give you maximum density. There's a mixing step. Here with a mineralizer, 1 to 3% CaO, the formation of the high temperature forms of silica. It's a dry pressing operation, so the water content is less than 5%. After you press it, you remove the water. There's most likely some type of organic binder mixed in with the water to give it some dry strength. And then these are fired at 50, and that converts the quartz to tridymite or cristobalite. Because there's a large phase, a large volume change with the phase changes, the heating and cooling cycles have to be rather slow. So the heating cycle for a silica refractory, when you from room temperature to 500 degrees C in 1 day, 24 hours, the next 150 degrees takes 15 hours. Then from the next 250 degrees is 17 hours. The next 200 is 10 hours. The next 200 is 10 hours. The next 50 degrees is 25 hours, and then 12 hours. 1350 to 1410, 60 degrees is 30 hours. It's really slowing down here because that's where the tridymite and cristobalite are. And then the last step here, another 20 to 24 hours. And then when you reach temperature in this area of approaching 1500 degrees C, you can hold it for 2 or 3 more days to make sure you've converted the quartz. Now you have cristobalite and tridymite. And then when you cool it down, you have to cool it down slow because of the displacive transformation. So this is the cooling schedule for typical silica refractory, cooling it down to 800 in 22 hours, to 600 hours, to 3 more hours, and 150 in 30 hours. And then the last step where the transformations are occurring, another 24 hours. So it takes a significant amount of holding that temperature and cool it back down around all these different reconstructive and displacive transformations. So how the microstructure forms, diagram A here, less than 750 degrees C. So we're heating this up to E. So you start out with large quartz particles. This would be a large quartz particle. They're in a matrix of medium and fine quartz particles, plus the mineralizer lime. So you have some medium particles in the matrix, and then fine particles of quartz and the mineralizer. So you start out with A at a low temperature. You heat it up to maybe 800 degrees C. Now the quartz and lime start to react at the particle surfaces. And these X's represent that reaction. This is a reaction at a quartz particle, a reaction at a smaller particle. So you start to form the lime silica glass. Then at C, as the temperature is raised, 1200 to 1300 degrees C, the surface of these quartz particles are now starting to convert to cristobalite because you're recrystallizing the cristobalite from the lime silica glass. So you're starting to form some cristobalite. And at D, you're at 1500 degrees C. So now the medium and fine quartz particles converted to crystal. You just have cristobalite in the matrix. Quartz particles are still converting to cristobalite. So this conversion layer is deeper on the quartz particles. And the lime silicate glass look as you dissolve more of the quartz. And finally, after a long time at 1500 degrees C, you have the structure in E here, a lime silica glass and silica crystallizing into tridymite. So you'll end up with a mixture of cristobalite and tridymite after some time at 1500 degrees C. So all the particles should now be converted from quartz to either cristobalite or tridymite. So that's what happens when you fire a quartz material, make a silica refractory. This is an SEM photograph of a sample that we looked at. It's a polished section. It's at 35X. The dark black spots are porosity. So there's probably 10 to 20% porosity in this material. The overall chemistry from the SEM analysis is 97% silica, 1.7% CaO, which is your mineralizer, which is added to this material. And then the impurities that were detected, 0.803, 0.2%, 0.3% Na2O. Keep in mind, this is a small chromate. It's not a bulk chemistry, it's a chemistry of this section. The overall chemistry of what we're looking at here at 35X, the medium gray colored material are the silica crystals. They show up as 100%. You can barely see their grain boundaries. And then the really light colored material is the silicate glass that was formed. So that silicate glass is about 78% SiO2 and 15 or 16% CaO. That's where your mineralizer is concentrated in this glassy phase. And then all the other impurities tend to dissolve in the glass, alumina, Fe2O3, the alkali, sodium and potassium, TiO2 and MgO. So that's what the silica microstructure looks like at a low magnification. If you increase the magnification to 750x, you're now looking at the darker gray area are all the silica crystals. So these lines that you see are the grain boundaries. These crystals analyze to 9% SiO2 and about 0.5% Al2O3. This area here, the brighter area, is your silicate glass. And there are actually two phases in the silicate glass. So the overall composition of this glass in this particular location was about 60% SiO2, 29% CaO, and then your other impurities are almost 5% alumina, 1.9% iron oxide. Your alkalis were at about 1.6 and 1.3, and you also have some TiO2 and MgO. So there appears to be two phases, a bright phase and a darker gray phase in this glass. The brighter phase is that crystal structure I mentioned, wollastonite, the calcium silicate. So wollastonite crystallized in this glassy phase. So this is the same magnification, and we're doing an elemental map, and we're looking at silicon first. So this mapping for this element, you can do any color, but this was yellow. So the brighter the color, the higher the concentration. So you can see where the silica grains are, it's very bright yellow. And then in this matrix phase here, the silicate glass phase, it's not as bright, it's a much lower concentration. We can also map some of the other materials, some of the other elements, and we mapped calcium, and it's in the area where the calcium silicate glass is, and this is purple. You can see that it's corresponds to the its location corresponds to these bright phases. So that's where the calcium silicate or wollastonite crystallized. Aluminum, that's this orange color here. That's between the wollastonite crystals. And your alkali sodium is also located in the glassy silicate phase. Also, the iron is mostly located, and this one is a red color. So the iron is located in the glassy silicates. So when you're all done with firing the refractory, these are typically what you end up in the microstructure: 30 to 60% trinamite, 25 to 50% cristobalite. You don't want any quartz, but you want to get less than about 2%. So quartz, either cristobalite or trinamite. The glassy phase may be 5 to 25%. And within that glassy phase, you may crystallize wollastonite, which is this calcium silicate, 1 to 2%. So that's where you end up when you produce a silica refractory. So for some of the properties, thermal expansion is important to consider because of the phase transformations. So each one of these quartz, cristobalite, and trinamite have their displacive transformations, which we went over. The high thermal expansions because of these transformations. And then there's low thermal expansion at high temperatures. If you recall, when we looked at thermal expansion of different materials, when we looked at silica, the expansion coefficient of silica as a function of temperature, there was a high expansion where these transformations took place, and then it tended to level off at the higher temperature. So the thermal shock resistance for quartz cristobalite and trinimite? Well, you have these displays of transformation, which cause these volume changes on the order of 1 or 2% that cause damage. So if you go through these transformations, you disrupt the structure and cause damage. So it has poor thermal shock resistance, low temperatures, and let's say less than 700 degrees C, where these trans. But once you get above that temperature, where the thermal expansion behavior tends to become flat, you have very good thermal shock resistance. The coefficient of thermal expansion really doesn't change. So at low temperatures, this material has poor thermal shock resistance because of the phase transformations. And at high temperatures, you have you've gone past the temperature of the transformation, so you have good thermal shock resistance. So this diagram shows the phases for silica. This is crystal density, and it's going from high density to low density in the vertical direction and temperature in the horizontal direction. So you start out with quartz. It expands normally. This is the alpha beta quartz transition from low quartz to high quartz. So there's a volume change. The volume change corresponds to a density decrease. And then from thermodynamics, at about 870 degrees C, you're supposed to go from high quartz to trinimite. But that doesn't happen because the kinetics are so slow. So what happens at higher temperatures in this band here of temperatures, your quartz goes to trinimite and cristobalite. And you go up here, you have that large volume increase, and now you go from a relatively high density to a low density material in this region. So now you either have trinimite or cristobalite, and then as you cool down, follow cristobalite, you go through the transformation, it becomes denser to the volume decrease on cooling. And trinimite, again, becomes denser. You go through the transformations here. So if you heat this up again, obviously you go through the same transformations, and then you have the volume increase and the density decrease. And vitreous silica has a flat change here. It's not crystalline, it's amorphous, so the density is really not changing. So that's what happens with the crystal density changes and temperature for all the different forms of silica. You can plot thermal expansion versus temperature. And this is only up to 1,000 degrees C. So you can see the phase transformations taking place, and then it tends to level off. And there's 4 different materials here. So one measure of the degree of conversion of quartz to either cristobalite or trinimite is a measure of the specific gravity. We mentioned that quartz has a higher density, and the other 2, cristobalite and trinimite, have the lower density. So when you can measure the specific gravity of the material after you produce low specific gravity, you've probably done a good job of converting everything to quartz, from quartz to cristobalite and trinimite. If the density is higher, there's probably still residual quartz. So if we look at D here, was this path. Here's your cristobalite and trinimite phase transformations in this here. But there's another transformation here that's pretty steep at 573 degrees C. That's your quartz transformation. So a high specific gravity tells you I have a lot of quartz present. And when you run the thermal expansion, this would be run in a simple push rod dilatometer, which we discussed. You have this displacive transformation and then the leveling off. So D is a poorly fired silica refractory. The other extreme, A, has the lowest specific gravity. So it goes through a bigger displacive transformation because there's more cristobalite and trinamite. So this curve is above this one. But at 573 degrees C, where the alpha, beta, and quartz transition takes place, there's really nothing happening there. So in A, you've converted everything from quartz to cristobalite. I mean, there's probably some quartz left, but it's too small to even show up in the expansion trace. In between are B and C. So the specific gravities are between A and D. So there's some quartz present. And you can see in B and C, there's still some quartz present. So that's what the thermal expansion looks like. You have some phase transitions for cristobalite and trinamite, and then you tend to level off, and hopefully you have no quartz present. So I showed this diagram the first day, linear expansion versus temperature. I mentioned that MgO was the highest in terms of thermal expansion. Silicon carbide would be one of the lower, and this diagram shows some aluminum materials. Noted the higher the alumina content, the higher the expansion. But this is what silica looks like. This is the transformations, cristobalite and trinamite, and then it tends to level off because of the open structure, which allows vibrations to take place in open spaces, and it doesn't really exhibit much thermal expansion. So because of the high thermal expansion here, you have to run heating, it's subject to thermal shock damage. But once you're above this temperature, it's relatively good in thermal shock. We mentioned the development of liquid phases that occur rapidly at some temperature. So the hot load and creep in this material are excellent. So hot strength, high capability, good creep deformation resistance, up to a point within a few degrees of where it melts. And that's a function of how many impurities are present. So it can support a load 50 psi up to 1650 degrees C. But as soon as you exceed that temperature, all these properties degrade rather quickly with the liquid formation. So the creep increases, the hot strength and hot load decrease also. Silica has corrosion resistance when in contact with an acid slag. So we went over some equations to calculate like a V ratio. So if you have an acidic slag, which is high in silica, phosphorus, low in MgO and CaO, silica is good in corrosion resistance. The thermal expansion of fused silica, we mentioned that quartz can be melted and you can form a glass. If you don't crystallize it, you form fused silica. So it exists in a glassy form. So it's amorphous, it's not crystalline. And that has a low density, an open structure, a random glass structure. So it has a low thermal expansion coefficient from room temperature to 1,000 degrees C, and the average coefficient is 0.5 times 10⁶ per degree C. Because of this low thermal expansion coefficient, the fused silica version of SiO2 thermal shock resistance up to this temperature. Above 1,000 degrees C, maybe approaching 1,200 degrees C, the glass starts to crystallize into cristobalite, and it is no longer a glass. So the thermal shock resistance changes at that point. You now have a material that's partially crystalline. So I also showed this diagram of thermal expansion versus temperature for different refractories. And on this diagram, this is the expansion of a silica refractory that's composed of tritonite and cristobalite. This is the phase transformation. This is where it levels off. Comparison. This is 19 down here is the fused silica, the material. It tends to soften and melt and is no longer a structural refractory when you hit 1200 degrees C, plus it also crystallizes. So you can see the big difference between the two materials and their thermal expansion behavior. Silica refractories are mostly used in coke ovens. So they line coke ovens. Coke ovens are in steel plants where they're converting coal to coke to use in a blast furnace to reduce the iron ore to iron. So there's coke ovens, and they also use in glass tank crowns. So the roof of a glass tank may be made out of silica. And then this is just a few silica material. These are all about 110 or so, 120. These materials have a porosity 20, even as high as almost 30%. The glass refractory porosity, you try to, if you have a glass, you want the lowest porosity to prevent corrosion in the roof of the glass tank. This is a fused silica product where it's been rebonded, so there's some porosity. So fine particles of silica were pressed into an object and sintered at a low temperature. The apparent specific gravities, we've mentioned these are about 2.3 or so for a fired silica brick and closer to 2.2 for fused silica. These are typical coal crushing strengths in PSI for refractory brick, 1,000 for these two. And this one, because it has lower porosity, we mentioned porosity lowers mechanical properties, so decrease the porosity, the strength goes up. The fused silica is also about 5,000. And here are the chemistries. The coke oven silicas are about 95%. The glass crown is a little purer, 96%. And the fused silica is closer to 99%. Because there's no CaO, 3%, 2.5%, 3% CaO in these refractories for the mineralizer, it's not present there. And some other impurities that are in Fe2O3, usually from 1%. So those are typical properties for a silica refractory. And we'll talk about the applications and what these furnaces look like on the last day. So there's an ASTM test, it's E794, and because phase transitions that take place in quartz, cristobalite, and tritonite, I put this test here. So have a test, so it's a method of measuring where these transformations take place. So it detects exothermic and endothermic changes of a test sample relative to an inert sample as a function of temperature under a controlled atmosphere using a DSC, which we talked about a little before, a differential scanning calorimeter, a differential thermal analyzer, which is a DTA. So we'll concentrate on a DTA in this particular test. You can also detect the phase transition, or you can detect where a material melts, can detect where it crystallizes. You can also pick up the glass transition in a glassy material. You can see where a material evaporates, or you can see where it decomposes. So all of these different types of reactions take place in refractories, and This is a useful technique to see what happens when you heat up a material. Terminology, this would be the heat flow, and this would be the temperature. So you're increasing the temperature of the sample, and you're monitoring the heat flow in that sample. If it goes up in the positive direction, it's a reaction, it's giving off heat. If it's in the negative direction, it's an endothermic reaction, it's taking up heat. So let's say you start out with a material at this point here at some temperature, and you heat it, and all of a sudden it starts to melting peak. It's endothermic. You have to add heat to cause the material to melt. So you get a sharp peak here, and then it's melted, and you continue on up after it's melted. Then if you cool it down, you reach a point here, it's a little bit undercooled, you'll have crystallization, and you get crystallization is exothermic in this direction, and then it's and when it's finished, you go back to your baseline. So you have a melting peak and a corresponding crystallization peak. So at this point, Tm is the onset of melting. That's basically the melting temperature. And Tn is the onset of crystallization. And that's basically the crystallization temperature. There's some width to these peaks because your sample's in a crucible. The reaction takes place at the surface of the crucible, and there's a thermal gradient in these crucibles. So it takes a little bit of finite time for the temperature to become uniform and the reaction to completely take place. But this is your melting point, and this is your crystallization point. So very simply, the heat flow or temperature change of a test sample is compared to that with an inert sample during some program change in temperature. So you can heat it, you can cool it. You usually do this under a controlled atmosphere. You can do it under an inert atmosphere or an oxidizing atmosphere. And you generate a change at your curve versus your heating rate, that temperature curve, whatever your heating rate you choose to run. So you get your endothermic or exothermic changes as a function of your heating temperature. So you have heat flow or temperature change of the sample. They're not really, they're constant. The heat flow or temperature changes are constant until a thermal event occurs. So if it's endothermic, the temperature of the test sample relative to the inert sample is lower. So the temperature of the test sample starts to lag behind the temperature of the inert sample, and that produces a minimum in the delta T versus temperature curve, your heating rate curve. So you get an endothermic peak because you're having to add energy to your sample for whatever reaction is taking place. In an endothermic reaction, the temperature of the T is the temperature reference. So now you have a maximum in the delta T versus your heating temperature curve. So you're giving off heat in this case. Also, the area under these curves, whether it's endothermic or exothermic, the area under these peaks is related to the amount of heat that's absorbed or given off, and that's your enthalpy delta H of whatever thermal event is taking place. So you can calibrate these pieces of equipment. You can calibrate a DTA and get this heat change, or the DSC, which we talked about earlier, measures that heat change directly. So it's an important test because it's a rapid test for determining transformations, melting temperatures, crystallization temperatures. It provides information on how a test sample changes during the thermal processing. So all the fired refractories are thermal processed. And in a room temperature castable, it's going to go through a thermal process in use. So this test really can tell you a lot of information. It can tell you when materials melt. It can tell you when a material forms a new compound. It can tell you when the material densifies and sinters. So it gives you a great deal of information about temperatures of reactions, and it is based on the thermodynamic and kinetic um, theory behind these reactions. The thermodynamics is going to tell you when a reaction takes place, and kinetics is going to tell you how fast. So you can use this type of test to determine the kinetics of a reaction. When you use this test, you have to be aware of some issues. The sample has to be homogeneous because you're using very small samples, milligram samples. So for a refractory, which is heterogeneous, again, for this test, you want to grind it to fine powder to get a uniform sample. You have to be aware something could be becoming volatilizing. So you want to make sure there's no toxic or corrosive volatiles that can be released during heating. You can actually vent the exhaust gas so that you avoid toxic materials. And the containers and crucibles that are holding your samples, whether it's the inert sample or unknown sample, has to be inert. So your test sample is between 10 and 500 milligrams of powder. So a half a gram is a large sample. I mentioned the samples have to be homogeneous and they can't react with the equipment, especially the sample holders or crucibles, so they can't be corrosive to the equipment. And you want to balance the masses. So the inert reference sample should have the same thermal mass as the test sample. So the thermal mass is just the heat capacity times the weight. And you want to balance these thermal masses because if they're not balanced, you'll have what's called baseline drift. So the baseline will drift up and down if the thermal masses aren't balanced. The inert reference sample is usually alumina. It can also be silicon carbide, especially if you're using an inert atmosphere so you don't oxidize the silicon carbide. Or another inert sample is MgO. We always use alumina. And this is how you balance the thermal samples to minimize the thermal drift. You have your inert reference material. In this case, let's say it's Al2O3. You know the heat capacity, the average heat capacity over this temperature range. So the heat capacity times the mass equals the heat capacity of the unknown times its mass. Well, you always know the mass of the unknown. You can weigh that. You may not know what material it is. So if you know what material it is, you can look up the heat capacity. If you don't know what it is, you have to guess. The thermal masses to eliminate or try to control the thermal drift. The equipment thermal analyzer is a furnace that of controlling a heating and a cooling rate. And there's an environmental chamber if you want to control the gas atmosphere. You have to have a temperature controller. Usually these tests are run about 10 degrees C a minute. You need to measure the furnace temperature. So you need a decent temperature sensor. It's a thermocouple. And then you need a differential sensor, which is detecting the temperature difference between the test sample and the inert sample. And then you have to record what's going on, these temperature differentials and the heating rate. So the differential temperature is recorded on the y-axis, and the heating rate temperature is recorded on the x-axis. So this is a schematic diagram of a DTA. The or the heating elements, so your furnace is up here. And there's two that extend into the furnace. One is supporting the sample and one is supporting the reference. So there's a small crucible sitting on top of these rods. They're usually made out of aluminum. And there's holes in the rods that allow the thermocouples, the platinum wires, to go through the rods up to the bottom of each crucible. So this would be your test sample thermocouple, would be your inert reference sample thermocouple. So if you're measuring this voltage, VTS, that is actually the sample temperature. If you're measuring this voltage, VTR, that's actually the reference sample temperature. But if you're doing a differential measurement, this one, V delta T, from this location across to that thermocouple, you're now getting the difference in temperature between the test sample and the inert reference sample. So that's why it's a differential thermal analyzer. So you're measuring three temperatures here: the temperature of the sample, the temperature of the reference, and the sample temperature, the difference in temperature between the two. You also have another thermocouple in the furnace for the couple. So that's what DTA looks like. So you simply load the test sample on the reference, inert reference sample of known weights into the crucibles. You can use a platinum crucible. You can use alumina crucibles, which are going to be disposable. Platinum crucibles can be cleaned. You purge the chamber with the desired gas phase if you want to. Otherwise, you can use air for oxidizing. You don't have to run a gas through it. Heat at 10 degrees C a minute and cool at the same rate. You have to heat relatively fast to capture the reactions. If you heat too slow, you'll get a very narrow or shallow peak. Heat at this rate, you'll usually get a good sharp peak. So a typical result, this is exothermic, this is endothermic, and this is temperature. CaMg, CO3, that's dolomite. That's a refractory material we'll talk about on Monday. It's a solid solution of carbonates. CaCO3 and MgCO3. There's two carbonates in solid solution. So as you heat it up, you can see that in this case, there's some baseline drift. And here's a endothermic reaction. There's some magnesium carbonate that's not in solid solution. So it decomposes to MgO and CO2. So that's happening right there. And then you keep heating it up and you get another endothermic peak. That's the decomposition of MgO. So that's the magnesium carbonate to MgO and CO2. So that was the magnesium carbonate in solid solution in the dolomite. Now you're just left with calcium carbonate, and that decomposes at a higher temperature. So you heat it up to a higher temperature, and then you get another endothermic peak for the calcium carbonate decomposition. So this tells you a lot of useful information. If you heat a dolomite as a function of temperature, you can see where the reactions take place. So your final product is MgO and CaO, and that's your refractory product. This crystallizes a lithium aluminum silicate glass. Again, it's exothermic versus endothermic as a function of temperature. There's not very much baseline drift here. So as you heat up, you see a little change in slope there. Well, that's the glass transition. It doesn't show up automatically like these other peaks, but it is there. And then this is a glass ceramic, so it crystallizes. So this is a crystallization peak in the exothermic direction. And if you keep heating, at some point, that crystal is going to melt. You get an endothermic peak, and now you've changed the either the heat capacity or the contact with the crucible, and now you have a lot of baseline drift. So there's an example of a glass transition, a crystallization peak, and a melting peak. So we were looking at some refractory materials, some fluxes that might be used in an aluminum reduction furnace. So you want to look at where the flux melts. You want to make sure it melts in the proper range. So the arrow in the horizontal direction is melting, and right, and from right to left it's cooling. So here's your delta temperature difference. Here's your temperature. So we heated this to about 850 degrees C at heating rate of a minute in your atmosphere. So you see there's two melting peaks, one here and a second one at a higher temperature. So there's two different crystals that are melting at two different temperatures. You can, if you don't know what these are, flux material, you can do an X-ray diffraction for these peaks, what crystalline phases are present and what's disappearing. And on cooling, you have the crystallization peaks, the exothermic peaks. So to get the melting or crystallization temperatures, you take a straight line and you draw the slope just before the reaction takes place on the baseline and then on the peak. And where those two slopes intercept, that is your melting temperature. In this case, it was 510 degrees C. And then that one crystallized on cooling, you make the same tangents and you get a temperature of 40. And the other one, the one that melted at the higher temperature, if you draw the tangents, the melting temperature is 700 degrees C. And then when you cool down, the crystallization temperature, it's a little undercooling, is 685 degrees C. You can pick up phase transitions, crystallization points, melting temperatures. So it's a very useful test to try to figure out what's going on in your refractory material. That in combination with the thermal expansion dilatometer type test, you can set up your heating schedule to sinter or fire your refractories. The other test I wanted to talk about for in this session was ASTM C987, and this is vapor attack in a furnace superstructure. So this would be vapor attack on a silica refractory in a glass tank furnace. So it compares the behavior of refractories in contact conditions, simulating glass melting, or any other application where any refractory can be exposed to some type of vapor from a raw batch, from molten glass, from fuel contamination. But it's primarily set up as a silica refractory. So in a glass tank, you have a lot of alkalis present. They vaporize, they diffuse to the furnace roof, and they give rise to what's known as vapor attack. So this test accelerates service conditions for determining to fluxing, loading, shrinkage, expansion, mineral conversion, disintegration, whatever is happening when that phase condensed refractory. So it provides a guide for evaluating the resistance of refractories in glass melting superstructures to vapor attack, and most superstructures are made out of a silica-based refractory. And you can use it to evaluate refractories in any other application where there's a vapor attack issue. So the sample is this rectangular prism. It's 55 millimeters by 55 millimeters in cross section, about 20 millimeters thick. And And you're going to place it on top of this dense alumina crucible, which is a little smaller diameter than 55 millimeters. And you're going to fill this crucible with the volatile material after you place the refractory block on top. You need an electric furnace to run this test with a stable temperature distribution. So here's your alumina. We fill it halfway with thin. This is the rectangular prism sitting on top of the alumina crucible, and another larger crucible to give it stability so it doesn't tip over. So you pick a reactant such as the vapor generated during the test is similar to that generated in service. It could be a carbonate, sulfates, borates, halides, all different components of a glass. You fill the crucible to about, you pick a test temperature that you think is appropriate to the reactant and trying to simulate your service environment. And you pick a time duration. They're usually around 24 hours. So this is a sample. It's 50 millimeters by 50 millimeters by the thickness, which is 20. And that's before testing. And this is what happens after testing. This is the ring that's generated where the crucible was in contact with the sample. So you have what happened here. You could examine it in many ways. The test really doesn't give you an exact method of examining this. It tells you to photograph it and visually observe. You can measure a change in a sample dimension. If the vapor diffuses into material and causes size, you can measure the sample dimensions. You can measure the pickup by the weight gain. You can section the sample, measure the cut in the refractory, the amount of material that disappeared. You can measure the penetration of the vapor, and you can also do a cross-section and do an SEM study and understand what exactly is going on. So here's the sample after it's cut in half. You can see there's a little bit of cut. You can see there's some bubble formation on a glassy surface layer that formed, and you can see another layer that's been penetrated. You can cut a section out of this and put it under an SEM and really understand the chemistry and what exactly is being attacked and what's happening. But the test really only tells you to cut it in half and take a picture. The typical ASTM test. So a report might look something like this. The reactant here was a sodium carbonate, which is a typical component in a glass batch, was held for 48 hours at 2600 degrees F. So there's two samples here, the dried and fired and after test condition. So the dimensions of the samples were measured, the weights were measured in the dimensions. So they gained a little bit. So they're a little bit longer, 0.47 the length, 0.47 in the breadth. The change is about 6%, and the weight gain is about 1%. So that goes through the silica refractories and a couple of ASTM tests that help you you heat these different materials. So one is the DTA and one test. So I think what we'll do is we'll stop here, and after lunch, we'll add alumina to silica, and that's a very common refractory material, the alumina silica refractories. And we'll again look at the raw materials, the phase diagrams, how they're made, and some of the important microstructure features affecting the properties. And I think I have one ASTM test in here on CO disintegration. Alumina silica refractories are used in blast furnaces and other applications where CO gas is present, so they're subject to attacked by a CO gas. So we'll do these aluminum silicate materials and I think one ASTM test. Now I think there's two ASTM tests. There's the PCE test, which is the pyrometric cone equivalent, which we'll go over, which is used to characterize these materials also. So we'll do this after lunch. So this next session is on alumina silica refractories. And we'll follow the same format we did as this morning, our raw materials, phase relationships, processing, and microstructure and properties. So this is a table containing raw materials for the alumina silica minerals. The minerals are fire clay based. They're clay minerals. A typical example is kaolinite. It's a hydrated aluminum silicate, so it's Al2O3, 2SiO2, 2H2O. It has theoretically 45% alumina. So we're going up in alumina content as we go down this table. Sillimanite, kyanite, and andalusite all have the same formula, Al2O3, SiO2. There's 65% alumina. The next one is mullite, 3Al2O3, 2SiO2, that has 75% alumina. Then the hydrated aluminas, momite, dispore, and gibbsite, all have 1 or 3 H2Os attached to the Al2O3. They're 100% alumina after you dehydrate them. And then corundum, Al2O3 is 100%. Mullite, dispore, and corundum are very scarce minerals. So they're if you want to make a mullite raw material, it's going to have to be a synthetic material. Now all these minerals have impurities. So these are the same minerals, and the impurities, when you have impurities, you're going to have a range of alumina contents. So clay may be 25 to 45%, sillimanite 45 to 65%, kyanite 65 to 75, andalusite 65 to 75, mullite's the same, 65 to 75, and then the hydrated aluminas, baumite, dispore, and gibbsite maybe 75 to 90%, and corundum is 90 to 100%. So we'll look at the clay minerals first, and they're a combination of 2 layers. The first layer is a silica layer. So there's a silica tetrahedron. The silica is at the center, and the 4 corners are oxygen. So the black circle is silicon, the open white circles are oxygen. This dotted line is a unit cell of the clay structure. So that unit cell just repeats throughout the structure. So the basic chemistry of a unit cell is Si2O5. So these tetrahedra are joined at the corners by the oxygens. So that's one layer. The other layer is the alumina layer. So the black circle is aluminum. It's sitting in the center of an octahedron. The open circles are oxygen. And then the double circles are the OH groups. So the aluminum is sitting in the center of an octahedron, and the corners of the octahedron are oxygen and hydroxyl groups. The dotted line shows another unit cell that repeats to make the structure. And the chemistry of that unit cell is ALO-OH2. So there's at least 3 different clay groups that we can list. So clays are hydrous aluminosilicates. They develop a great deal of plasticity when mixed with water. And There's three structural groups. The first is the kaolinite group. And I just mentioned kaolinite, Al2, Si2O5 with 4 OH groups. Halloysite is the same formula, except now there's 2 waters attached to that structure, 2H2O. There's the montmorillonite group. Now, montmorillonite has a sodium and magnesium substitutions on the aluminum sites. And it also has an attached water, H2O. Paraphyllite is Al2, Si2O5, that's 2 times plus OH2. And then the third group is the illite group. Mica, Al2K, Si 1.5, Al 0.5, oxygen 5, that's 2 times that group, OH twice. So now you have potassium substitutions for the aluminum sites and some aluminum substitution on the silicon sites. And illite is this long formula. It's hydrated with an H2O, but it has magnesium and potassium substituted on aluminum sites and aluminum substituted on a silicon site. So those are the 3 major groups of clays that can be used for raw materials. The most common one is kaolinite, and kaolinite has about 40% Al2O3, about 47% SiO2, and the balance before it's dehydrated is about 14% water. So this is a better view, I think, of the clay layered structure. These small open circles are silicon. These small open circles in the top layer are aluminum. So the bottom layer is the silica layer. The top layer is the alumina layer. And the open circles, the large open circles are oxygen. And then the circles with the pattern in it are the OH groups. So you have a layer of the silicon tetrahedrons and a layer of the aluminum octahedrons, and that forms a layer, one layer in the kaolinite group. So this diagram shows 3 different groups, kaolinite, montmorillonite, and mica. So here are your 2 layers, the silicon layer and the aluminum layer. The black dots are silicon, the open circles are oxygen. So here's your tetrahedrons. And then the octahedrons, this is aluminum, and they're attached to the oxygens and the OH groups. So there's your layer, and then you have multiple layers, and when you hydrate it with water, you develop plasticity. Water goes between the layers. Montmorillonite has 2 silicon layers. So there's a layer on this side of silicon, an aluminum layer, and another silicon layer. So it also has aluminum substituted for silicon. So this circle that's half dark and half light is where a substitution might take place. And it also has magnesium substituted for aluminum, and that's that circle here, which has 2 colors in it also. And the open circles are oxygen, the double circles are the OH groups. So it's a layer of a silicon tetrahedra, a layer of the aluminum octahedra, and another layer of the silicon tetrahedra, separated by water layers that develops plasticity. And then mica is similar to montmorillonite. It has a double layer of silicon, one on top and one on bottom of the alumina layer. And in this case, you have some substitution also. You have aluminum on the silicon sites. You have aluminum in the center, and then you have potassium between the layers. So that's what that structure looks like. So they're combinations of different layers with different substitutions to make up all these different clay minerals. So a typical chemistry, a Georgia kaolin and a Kentucky ball clay. Um, when you dehydrate it, you drive off the water, so there's a loss on ignition, LOI. It's about 13% in this kaolin and about 11% in the ball clay. This is the silica content, about 45% and about 56%. Alumina is lower, 38% and 28% here. And then you have your normal impurities, the Fe2O3, TiO2, CaO, MgO, and the alkalis, K2O and Na2O. So they make up the balance. And the Georgia kaolin, if you X-ray it to see what phases are present, you have kaolinite, the clay mineral, but you also pick up some quartz. And in the Kentucky ball clay, you have kaolinite, you have some quartz, and you have another clay, montmorillonite. So there's 3 different minerals here and 2 here. But the majority of the phases present are the kaolinite clays. So what happens when you apply heat to kaolinite, and we'll just look at this case greater than 1400 degrees C. So we just heat it up to a high temperature. This is the formula for kaolinite. It decomposes, you dehydrate it, the water comes off, so the H2O is gone. Then you have alumina and silica left. You form 2 other compounds. You form mullite, 3Al2O3, 2SiO2, and then you have 4 silicas. Depending on the temperature and how long you hold it, it may be in crystalline form cristobalite, or maybe amorphous, or something in between. So you end up with 63% mullite and 37% silica. Those are the percentages of the phases, and kaolinite has about 46% alumina and 54% silica after you drive off the water. So these are the final products. And this slide shows you how you get there. So again, application of heat to kaolinite. You start out with your kaolinite clay. When you reach the temperature 400 to about 525 degrees C, you dehydrate it, so you drive off the water. So now you have something that's known as metakaolin. It's an amorphous material. It's no longer crystalline. So it's Al2O3, 2SiO2, and you continue to heat it to a higher temperature, over 1000 degrees C, maybe up to 1100 degrees C. And now you develop mullite, and that's an important refractory phase. And that's 3Al2O3, 2SiO2, and you have some SiO2, which is amorphous, it's not crystallized yet. As you take it up to higher temperatures, over 1200 degrees C, you still have mullite, but now the cristobalite starts to form. And if you take it to an even higher temperature, you still have mullite, and you may have crystalline cristobalite, or you may develop some more amorphous silica, some combination of amorphous glassy and crystalline silica. So that's what happens. That's the sequence when you heat up a kaolinite clay, and you want to end up with this compound mullite. The next group consists of sillimanite, kyanite, and andalusite. Those are the anhydrous aluminosilicate minerals. They're all 1-to-1 alumina to silica, so it's Al2O3 SiO2. This is orthorhombic, this is triclinic, this is orthorhombic. These 2 have the same crystal structure, but they have different bond lengths, or the length of the crystal cells are different. So here's a kyanite from Virginia, a sillimanite from South Africa, and another andalusite from South Africa. They're not hydrated minerals like the clay, so there's very little loss on ignition. Perhaps an impurity or an organic material is being driven off. The kyanite is about 40% SiO2. This one is about 20% the sillimanite, and the andalusite is about 39%. The balance is primarily alumina, so the kyanite has about 59%, the sillimanite has about 75%, and the andalusite has about 59%. And all of these minerals are going to have the same type of impurities: an iron oxide, a titanium oxide, calcium and magnesium oxides, and the alkalis, sodium and potassium. So the Virginia kyanite, when you x-ray it, it's the mineral kyanite. This one, the sillimanite, when you x-ray it, you get sillimanite. You also get some rutile. There's a fairly high TiO2 content, and there's also some corundum present. And that's why this number is fairly high, because there's corundum present that enhances the alumina content. And that's why the silica content's lower. And then this andalusite, when you x-ray it, it's just a mineral andalusite. So when you heat up one of these minerals, the anhydrous aluminosilicates, whether you start out with sillimanite, kyanite, or andalusite, it's Al2O3 SiO2. They convert to mullite and cristobalite. But unlike the clays, the mullite content is much higher. It's 88% mullite and only 12% cristobalite, or the amorphous version. So these minerals are much higher alumina content than the clay, so they're more refractory. The alumina content's closer to 63%, and the silica is about 37%. So when you convert any one of these three minerals to mullite and cristobalite, there's a big density change. So this is the starting density. So sillimanite is 3.3, and that's grams per cubic centimeter. Kyanite's 3.7, andalusite's 3.3. These decompose at these temperatures, and they decompose to mullite and cristobalite. So mullite relative to these minerals is 3.16. Cristobalite's only 2.33. Mullite melts at about 1850 C, and cristobalite is 1723 degrees C. Silica glass, if it's in the amorphous form, is 2.2. So you have low density products. That means when you go through that conversion, there's a volume expansion upon heating and sintering. So if you have this kind of mineral, perhaps bonded with a clay matrix, what's going to happen is when you sinter that, it's going to offset shrinkage of the clay and maybe give you some volume stability. And we'll talk about this on the last day, how you can use these reactions to control the reheat, either increase or decrease in an actual application, and why you may want to have it increase. Mullite is a mineral by itself. Itself is very scarce. Again, mullite is 3 aluminas to 2 silicas. It's orthorhombic. Stoichiometric mullite is 71.8% Al2O3 and 28.2% SiO2, and it melts at a higher temperature, 1850 degrees C. Mullite's a scarce mineral, so it's a synthetic man-made material. You make it from a mixture of bauxite, an alumina source, and clay and alumina silica source. So you can have a sintered synthetic material or a fused synthetic material. The sintered material is going to have open porosity. The fused material is going to be a dense, basically low porosity material. So the sintered materials, you calcine the mixture of bauxite and clay. You form it into some kind of pellet, and then you sinter it at about 1800 degrees C to form mullite, and you crush it and size it. And the fused ones, you melt it in an electric arc furnace at a temperature greater than 2000 degrees C, and you pour it into molds, and it recrystallizes upon cooling, and now you have dense mullite crystals. So dense crystals are an advantage over sintered crystals because there's very little porosity, and that enhances the corrosion resistance of that material by eliminating the porosity. This is just a flow chart for forming synthetic mullite in the sintered version. You have some form of calcined alumina and a clay. It's mixed and then formed into some type of granular material or pellets. It's dried. It goes through the sintering heat treatment process. These pellets that come out are then crushed. You can do some purification. Maybe you want to remove some iron. You screen it into the appropriate sizes, and that's your product. Different sizes of the mullite. The flow diagram for fused mullite, you're starting out with higher purity materials here. You maybe have a high purity calcined alumina and a silica sand. You melt it in an electric arc furnace. You pour it into ingots, usually carbon type molds. You crush that material. You can further purify it by removing iron. And then goes through a screening process for a final product, or you can mill it finer, screen it, and have the final product. So this gives you a dense, basically pore-free material. So this would be the chemistry of a sintered mullite versus a fused mullite. The silica range is about 21 to 26 for the sintered one and 23 for fused. And the range for alumina in sintered is maybe 71 to 77 and about 76 for the fused version. These are the impurities. So if you start out with higher purity materials, these values are going to be pretty low. Some of them are just trace, but these are your normal impurities that you're going to see in these alumina silica materials. The bauxites are the hydrous aluminum materials, boehmite, dispore, and gibbsite. Boehmite and dispsite and boehmite and dispore have one H2O, and gibbsite has three H2Os. The first two are orthorhombic. The third one is monoclinic. Once you dehydrate it and remove the water, they're 100% Al2O3, assuming no impurities. Pure alumina melts at 2050 degrees C, so it's the high temperature material. So hydrous aluminum minerals, the bauxites. Here's one from Guyana, and here's one from Brazil. They're both about 90% alumina, 5 to 8% silica, and then you can see the impurities. They contain quite a bit of rutile, about 3% here and 2% here. Iron is pretty high, 1 and 2%, and everything else is fairly low. So if you look at the crystalline phases that are present, both are corundum. The majority of the material is corundum, and there's some rutile also, which is the TiO2. The corundum mineral is scarce, Al2O3. Its crystal structure is hexagonal. Alpha alumina is a high temperature form. Again, it will be 100% alumina, assuming no impurities, and the melting point is 2050 degrees C. Corundum is a synthetic mineral. It's produced from bauxite. And then, again, just like for mullite, there's two versions, a sintered version and a fused version. You're going through the same processes. For the sintered version, you calcine the material, you form it into pellets, you sinter it at a high temperature, and this time it's sintered at 2000 degrees C. It's crushed, sized, and now at that temperature, the alumina, the hexagonal crystals grow into large tablets. So it's known as tabular alumina because of the large crystal size. The fused material is melted and they recrystallized upon cooling. And in that case, you're going to form very dense alumina crystals. So the flow diagram for sintered alumina, you're just starting out with an alumina. It's crushed and formed into some type of pellets. It's dried, sintered. The pellets are then crushed. Impurities can be removed, such as iron, and it's screened and milled and screened again. So you have a range of particle sizes as the output. The fused material is simply melted in an electric arc furnace, poured into an ingot, crushed, may go through a cleaning or process where the iron level may be reduced. They can be screened for coarse particles and milled for finer particles. Typical chemistry for tabular versus fused alumina. They're both high purity, 99.5% alumina. The balance is mostly SiO2, Fe2O3, and sodium. Everything else should be there in trace quantities. So they're high purity materials. The high melting temperatures help to drive off volatile components like the alkalis. So the phase diagram is alumina SiO2 silica. So it turns out between 0% alumina and 71.8% alumina, liquid develops at this temperature, 1595 degrees C. 71.8 is the amount for a mullite. So above 71.8 Al2O3 to 100% Al2O3, liquid develops at a higher temperature, 1840 degrees C. So you can see this in the alumina silica phase diagram. This is weight percent Al2O3 to 100%. Silica goes from 0 to 100 in this direction. So this is pure silica. This is pure alumina. And we have temperatures in Fahrenheit and degrees C. 71.8 is mullite. So I mentioned that below the mullite composition, below 71.8% alumina, here is your melting temperature, and this is in degrees F, 2903. That's a little less than 1600 degrees C. But if you're above 71.8% in alumina content, you're up here at 3344 degrees F, or higher than 1800, maybe 1840 degrees C. So to the left of the mullite material, you have basically, as you heat it up, you have tridymite plus mullite, then you have cristobalite plus mullite, and you have mullite plus liquid in this two-phase region, cristobalite plus liquid over here, and you have a eutectic at about 5.5% alumina. And in this side, you have corundum, which is alumina plus mullite, and that goes to corundum plus liquid above 3344F, and the small section here would be mullite plus liquid. So your fire clays are going to be down in this region here, 20 to 40%. Alumina, your high aluminas are going to start around 50%. Once you hit mullite, all those higher aluminas are going to be much higher temperature materials. So this diagram really lays out the whole alumina silica system, and you can look anywhere on the system, see where your material melts, and then once it melts, you can use lever rules to see how much liquid forms in these two-phase regions that contain liquid. And this is just another diagram of the same thing, just a simplified version. And this is in mole percent. So it's 3 to 2. So here is the 60 mole percent Al2O3 or mullite. And again, you see the same thing, silica plus mullite going to mullite in liquid at about 1595 degrees C, and mulliting corundum going to corundum in liquid at about 1840 degrees C. So a useful diagram, you can see where you are based on your composition and how the melting behavior looks. So the fire clay refractories are less than 50% alumina. When you process them, you start out with a calcined clay and a raw clay. And the reason you use the calcined clay, it's pre-fired, it's already exhibited its shrinkage, it's sintered, it's dense. You use calcined clays in combination with raw clays to control the shrinkage after you fire it. If you use a raw clay, you would probably have excessive shrinkage and it would be hard to control the dimensions of the sample. So pre-fired clay, raw clay are crushed, screened to the appropriate size distributions that give you maximum particle packing. We'll talk a little bit about particle packing on the last day for refractory design. And then they're mixed. And then there's two ways to process this material. You can add a small amount of water, 5 to 8% for dry pressing, or a much higher water content, 10 to 15% water for an extrusion process. Remember, clay develops plasticity when mixed with water, so it's very easy to extrude. Whether it's dry pressed or extruded, you dry it and then you fire it. The firing temperatures are not that high, 1100 to 1500 degrees C. So a flow diagram for a dry pressing operation might look something like this. At the bottom, you have inspection of the final product, and if it's rejected, it goes back up here to the beginning, and they call it grog. Well, that's just the pre-fired clay, which is the scrap in this case, but it's pre-fired. And then you have your raw clays, you have different kind of flint clays, plastic clays, and they just go through a series of crushing and screening operations to you get a series of bins with different sizes. You proportion those sizes so that you have the right kind of particle packing for maximum density. At some point, it goes through a mixer where water is added, a dry press operation. Drying removes this physically held water. It's fired in a furnace and then inspected, and then the rejects are just recycled as the fired component. The other flow diagram is for extrusion. And again, the same thing happens here after inspection. The rejects are the fired product. That goes back up into the starting materials. And we can have the 4 different types of clays here. And same thing happens. They're crushed to appropriate sizes. They're sorted. They may be crushed again and screened to the appropriate sizes, stored in different bins and proportioned in the right amount in the different size distributions for the right particle packing. And now they go through a wet process where water is added. There's something known as a pug mill or a wet pan where the plastic mass is formed with the water. That goes into a screw-driven auger that extrudes the plastic mass. And sometimes it may be repressed because an extruded product may not be that dimensionally stable and you want to true it up, so you may repress it. It's dried and then fired and then inspected. So that's flow diagrams for fire clay type materials. When you go to alumina content over 50%, you're now using your calcined 1-to-1 ratio of alumina to silica. You're using this type of anhydrous raw material, and you're mixing it with a raw clay. And the operations are basically the same for all of these from now on for the rest of these high aluminas. The raw materials are crushed, screened to the appropriate sizes and mixed in the right proportions to maximize your density. A raw clay may be added in this mixing process. Dry pressing is usually 5 to 8% water. A drying step, and then it's fired. As you increase the alumina content, these temperatures are going to go up. So this is from maybe 1200 to 1600 for a refractory in the 50 to 60% alumina range. When you get up to percentages approaching 80% alumina, you're starting at your raw materials will be a mullite source, a synthetic mullite, or a synthetic alumina. And you may still have raw clay as your matrix bonding phase. So you crush materials again, you screen them. There's a mixing step again, dry pressing at a low water content, drying and firing. And now your temperatures are from 1500 getting up to 1700 degrees C to fire and densify these alumina silica, high alumina silica refractories. Now when you get up to compositions in the 90% alumina range, you're just starting out with your synthetic alumina, Al2O3. Again, you crush it, screen it, and mix it, press it at a low water content, and it's fired in this range 1500 to 1700 degrees C. And the last one here, the ones that are getting closer to 100%, you're going to have a calcined alumina, maybe the sintered tabular alumina, or the fused cast alumina. So higher purity materials, the same type of steps here, crushing, screening, and mixing, followed by dry pressing and drying. And now the firing temperatures are quite a bit higher, 1800 to 1900 degrees C, to process these high alumina refractories. So for the microstructures, we can make some generalizations. Room temperature, for all of these materials, you're going to have a crystalline particle bonded by either smaller crystalline particles, and that's known as direct bonding, or bonded by a glass, depending on the composition. So the higher alumina materials will be more direct bonding. The fire clay materials will be more glassy phase bonded. You're always going to have porosity. So then when you increase the temperature to a use temperature, the microstructure is going to consist of a liquid phase. That's a glassy phase that's going to be separating or isolated between the other crystalline particles. So you're going to have a glass or crystalline particles melt that form this liquid phase. The refractory properties, well, at room temperature, it's determined by the amount and type of crystalline particles, glass, and porosity. Glass is rigid, strong at room temperature. So the room temperature mechanical properties are going to be quite good. At high temperature, the properties are going to be determined by the amount and viscosity of the liquid phase that forms. So the more liquid phase, the properties are not going to be as good as a material with a lower liquid phase content. So if we look at fire clays, less than 50% alumina, and we consider their microstructures, well, at room temperature, you're going to have mullite. You're going to have the mullite crystals, you're going to have cristobalite, and they're going to be bonded by a glassy phase in the matrix. And the mullite forms long needle-like crystals. So the mullite crystals form an interlocking structure, which gives it some good mechanical properties. It's almost like a fiber reinforced composite. At high temperature, you're going to still have mullite and cristobalite, and now this rigid glassy phase is going to be a viscous glass. In the high alumina microstructures, greater than 50% alumina at room temperature, you're going to have corundum now, mullite, and cristobalite, and you're going to have glassy phase, but it's going to be less in volume than in the fire clay materials. And mullite still forms these interlocking needle-like crystals. High temperatures, you're going to have corundum, mullite, cristobalite, whatever glassy phase you have present, it's not going to be a viscous fluid. So this is an SEM micrograph of a fire clay refractory. Again, the black in these micrographs is going to be the porosity. This is 20x, and this particular fire clay refractory is 45% alumina, 52% silica, and these three materials are also picked up: TiO2, Fe2O3, and alkali K2O. You can see in this micrograph, you can see some outlines of some coarser aggregates. This is the pre-fired portion. You can see them, and then in between is the raw clay that's been sintered. Everything has the same chemistry, whether it's the matrix or the coarser grains. But basically, you have coarse pre-fired grains surrounded by a matrix of the raw clay that's now fired. So this is the same thing, same fire clay at 500x. This is a pour. Here would be another pour. These are a series of small pours. So this is most likely the coarser grain that's been pre-fired, and this is the matrix that develops from the clay after firing. There's a lot more porosity here. But if you look at the chemistry, since they're both the same clay, basically, they both have the same alumina content, around 44, 45%, silica about 49 or 51%, and the same impurity levels. So that would be a microstructure of a low alumina fire clay material. And I guess I have one more micrograph here at 3500x. This is just showing the detail. So you can see two phases here. The lighter phase are these elongated crystals. That is the mullite. And if you pick a spot on one of these, you get a 64% alumina, 31% silica, some TiO2, and some Fe2O3. So they're richer in alumina. And then if you look at a darker region, that's your silicate glass. That's only 28% alumina and 63% silica plus the impurities. So on a really fine scale, whether you're in the matrix portion or the pre-fired particles, this is what the microstructure looks like at a higher magnification. So this is a microstructure for a material that has a higher alumina content. Again, the black regions are porosity. And you can see here that this is a high alumina, about 91% Al2O3. So the overall this is the overall composition of this area: 91% alumina, 8% silica, and some sodium. You can see the coarse aggregate, the pre-fired aggregate. And just by looking at this, you can see the light porosity. You can almost see the individual crystals of alumina. So this is some type of calcined or tabular alumina. And the chemistry of this particular grain is about 97% alumina and 3% silica. The area between these coarser grains are the matrix areas, where you have a mullite and your glassy phase. So that has a lower alumina content, about 85% alumina and about 15% silica. So if you map the elements, if you map aluminum, And we're using green here for the color. The brighter the color, the higher the aluminum concentration. So you can see the coarse grains and the medium grains stand out quite well. And then the lighter, or actually the darker colored green that's not as bright, is the matrix. If you map silicon in blue here, you can see that the coarser grains are higher and the medium grains are higher in purity level. And then you can see that silicon is concentrated in the matrix area between all the medium and coarse size grains. So if we go to 1000X and look at this microstructure, this is one of the tabular alumina aggregates, a coarse aggregate. You can see the porosity that develops during sintering. You can't really see the individual crystals, but you can sort of see some of the grain boundaries. This is the matrix. It's 61% alumina and 35% silica with your typical impurities. So the way this one was designed was a tabular alumina aggregate, and they were trying to achieve a mullite matrix to bond the aggregate together. So some of the properties, if we look at thermal expansion, this is expansion or shrinkage versus temperature for a fire clay. So I've put this in a table here. From A to B is your normal reversible thermal expansion. From B to C, you start sintering the material, sinters at a really low temperature, and you start densifying it. Then from C to D, you have an irreversible expansion. What's happening now, you're forming mullite, and a lot of these clays have other elements present. They may have sulfur, organic material, which is some form of carbon, and they have the OH groups. So when you heat these up, they form gases. Sulfur forms SO2, carbon forms CO2, and OH comes off as water. So they expand. It's an expanding clay. So many years ago, when they first started using ladles, they used these expanding clays. So they line the ladle with bricks made of less than 50% alumina with clays with these impurities. So they expanded during use, and the joints between the bricks closed, and it prevented metal penetration. The only problem with these materials is their low temperature, and as the steel making process evolved over the years, you needed to go to higher temperature materials, so they became obsolete. But anyway, between C and D is where you may have a gas coming off causing a permanent expansion or a mullite formation. And finally, from D to E, you have another irreversible shrinkage. That's either due to sintering or viscous glass forming. So there's many different sintering mechanisms. Some are solid state, some are viscous flow. Either way, you're having a sintering process take place that densifies the material. So some of the important properties of a fire clay refractory: hot load and creep deformation. It's going to depend, the deformation is going to depend on the liquid phase formation. So you have some of your typical impurities, the alkalis, the iron oxides. They're going to lower the melting temperature. So the alumina content is important because the melting temperature is increased with alumina content. The impurity content is important because they're going to decrease the melting temperature as the impurity level increases. So your creep, your hot load, your hot strength are all going to depend on the amount of impurities and the alumina content. Sillimanite, kyanite, andalusite, the raw materials that are going to give you refractories in the 50 to 60% alumina range. When you talked about the thermal expansion behavior, you can tailor in an irreversible expansion, and that's due to the conversion of the low density to the lower density mullite at high temperatures. So you can tailor in a reheat expansion in these materials. The higher aluminum material, 60 to 80%, based on a synthetic mullite. The thermal shock resistance for this kind of material where you have mullite present is fairly good. You have good thermal shock resistance because the thermal expansion coefficient of mullite is only 5.3 times 10 to the minus 6, and that's per degree C. If you remember, alumina was about 8.5. So the low thermal expansion coefficient of mullite gives it good thermal shock resistance. I mentioned, and we saw some micrographs showing mullite needle-like crystals that interlock. Those interlocking crystals give it good creep resistance and good hot strength. And then the very high aluminum materials up to 99% alumina made with synthetic corundum. For the thermal shock resistance, it's got a lower thermal shock resistance compared to the mullite refractories we just discussed because the thermal expansion coefficient is now 8.5 times 10 to the minus 6. So it's quite a bit larger than for mullite. However, a high purity alumina has good creep resistance and good hot strength because it has a high alumina content. And again, because it has a high alumina content, it has good corrosion resistance, and it's a very hard material, so it has good abrasion resistance. So all of these refractories, when you start looking at a group of properties, you're always going to have trade-offs. So if you want a creep resistant, very strong material at high temperatures that is corrosion resistance, you're going to sacrifice the thermal shock resistance. So you can never design a refractory with all the properties maximized. You're going to have to compromise and maximize the properties that are the most important and try to maintain the other properties to an acceptable level. This table just summarizes the fire clays and the high aluminas. So we go from semi-silicas up to the super duty. So the use temperature goes up and the PCE value goes up. The softening points or the deformation points also go up in this direction. So we mentioned semi-silica, low duty, medium duty, high duty, and super duty. The PCE values, and there's an ASTM test C27 that classifies fire clays based on the PCE values. So in order to be a super duty fire clay, you have to have at least a 33 PCE, and a typical PCE would be 33 to 34. The high alumina class goes from 50 to 90%. We also have mullite and corundum. These are the PCE values that are the minimum values required to be in these classes. So a 70% alumina has to be at least a PCE value of 36. And these are the typical PCE value ranges for all of these materials, corundum being the highest melting material. The parametric cone for 42 cone is basically high purity alumina. So why these aren't here, and these are estimates, and we measure the PCE in our lab for materials. We go up to about a 36 or a 38. 42 is where aluminum melts. So if you put a parametric cone in a furnace that's pure aluminum and you want to melt it, and you're melting it in an aluminum furnace, you're going to melt everything, furnace and the cone. So you don't typically see these numbers here. They're estimates. But they were measured at one time to establish these standards. So as you go up in alumina, the PCE value goes up, and then the use temperatures go up. So there's a couple slides here of some different alumina content refractories and their properties. These are high duty and super duty bulk densities, and they're always reported in pounds per cubic foot, are about 130 to 140. And I keep mentioning the porosity in these materials. These are about 15 to 20%. We talked about the cold modulus of rupture, the bending test, 1 to 2,000 maybe. We talked about cold crushing, and it's always higher in compression than in tension. So these are maybe 3 to 8,000 PSI. We also went over the hot load test, holding the sample at 25 PSI for an hour and a half. And these were the hot load temperatures for these materials. High duty is usually 2460, and the super duty is usually 2640. And these are the percent deformations. These are a little more than 1%. This is about 0.6, and this is about 3.6. These are the chemistries, about 36% alumina for the high duty and 42% for the super duties. The corresponding alumina contents, corresponding silica contents, and then the impurities. And if we look at this one's 141. This is 133. This is not as strong, either in tension or in bending or in compression, but the chemistries are the same. This one has a much bigger hot load deformation. So we start out with something that's less dense. So it's not going to be as strong. It's going to have higher porosity, even though it's the same chemistry. It wasn't processed the same. And it may have been processed this way to make it weaker with more porosity to give it better performance in thermal shock. And hot load deformation here is probably a combination of sintering and deformation. It's probably densifying at this temperature. So you can play around with the densities and the porosities, and even with the same chemistries, control the strengths for different types of applications. The 50 and 60% aluminas, the density goes up to in the 150 pounds per cubic foot range. Typical porosities, they're getting a little stronger in bending and a little stronger in compression. The hot loads, these were run at, again, 2640, and the deformations are getting smaller because they're higher purity level, higher alumina content. A 50% alumina has 50% Al2O3 in it, and 60%, this one has 58. And it turns out that anything close to a 60% is called a 60% refractory. So if it's 58, it's still 60%. It usually, in the specs, you're allowed plus or minus a couple of percent. So the balance is silica and then your typical impurities. The next group are the 70 and 80% aluminas. And as you go up in alumina content, you're now going from 154 to 162 to 171 to 188. So the density is going up. Porosity levels are in the same range. Some of these strengths, depending on how they're processed, are getting a little bit higher than the fire clays. The compressive strengths are getting higher also. And you can see now the hot load temperatures are run at a higher temperature, 2910. This one's still 2640. And this is 2910, and this is 3100 F. So you can see what the deformations are. The lower deformations in the higher purity materials. And then these alumina levels correspond to 70, 80, and 90%. The balance is primarily the silica. And when they're in the 90% range for Al2O3, this one's approaching 190 pounds per cubic foot. This one's approaching 200 pounds per cubic foot. They're still processed with high porosities. Now the cold MOR is getting quite good. This one's over 3,000. This one's almost 3,000. And this is almost 98% alumina, and this is 99%. So that's an overview of the alumina silica type refractories, the raw materials, how they're made, their phase equilibria, and some of their properties. There's two tests I wanted to go over. We keep talking about the PCE test, the pyrometric cone equivalent. So we'll do that one, that's C24, and then we'll do a CO disintegration test. So in the PCE test, you determine the PCE value of a refracting material by comparing it with the standard pyrometric cone of a known value. It's useful for materials that have a silicate glass in the matrix, fire clay brick and mortars, high alumina brick and corresponding mortars, and high silica fire clay brick and mortars, all develop glassy phases and exhibit a deformation that takes place over time. When you have a refractory with a glassy phase, you're not really going to have a distinct melting or deformation temperature because of the glassy phase. The glass does not have a distinct melting temperature like a crystalline material, so it gradually becomes less viscous and deforms over time. So that's the way this test is set up, primarily for alumina silica materials, but you can use it for any refractory material. It still works. So you make a test cone from a refractory material and compare its deformation endpoint to that of a standard cone. The resultant PCE value is a measure of the use temperature or the refractoriness of the material. So the higher the PCE value, the higher the melting range. It's important because the deformation endpoint of a cone corresponds to a combination of temperature and work, or heat and work, and that includes the effects of time, temperature, and perhaps the atmosphere. PCE values classify fire clay and high alumina refractories. We just saw a table where there's a minimum value for each type of fire clay or high alumina refractory. PCE values can be used to identify variations in fire clay, mining control, and raw material specifications. So it's a quality control measure. You can use it at a clay mine. You can use it after you make a fire clay refractory. Most of the alumina silica refractories in their data sheets will have the PCE value. So it's a product specification. You start out with your sample, the alumina silica refractory, whatever it is, or a raw clay. You grind it to a -70 mesh. So you don't go real fine, but it's -70, so you do have some fines present. You mix that with an organic binder that does not contain any contamination like an alkali that'll affect the melting range. And you mold it into a cone, which is a truncated trigonal pyramid. This is what the pyramid looks like. And there's cones of different sizes. This is one about 1 inch long. There's some that are about 2 inches long. But the shorter ones are known as the PCE cones. You take these truncated pyramids and you mount them in what's known as a cone plaque. And it's just a cylinder, and it has holes in it where these cones drop in. So there's a triangular shaped hole. And then you heat this whole thing up and you observe it as you heat it. So in this cone series, you have some known cones. This is like a 29, a 28, there's 27, 26, 23, 20. And then you have an unknown. Then you have some higher numbers, 34, 35, 33, I guess a 32, a 31, and a 30. And then if there's no number, that's your unknown material. So they must have different, for in this illustration, different materials. And here's one that's bending over. So that's an unknown. This one is just starting to bend over, and this one hasn't done anything yet. So you compare the degree of deformation to a known material that has a known melting range, and you assign a PCE value to it. So you need a high temperature furnace. This test has a specific heating rate because it's a measure of heat work. So it's 270 degrees F per hour or 150 degrees C per hour. And it's an oxidizing atmosphere. So you cement the cones into a plaque, and I just showed that, what the plaque looks like. That's a high temperature refractory material. And the cones are not exactly straight up. They're at 8 degrees off the vertical, so they're 82 degrees with the horizontal. They're slightly tilted so that they gravity pulls them down when they start to deform. So in the PC value, you compare the deformation endpoint to that of the standard parametric cone. And the standard parametric cones are their deformations are tabulated. So you have a couple of different cases here. If the reference cone nearly corresponds to the test or the unknown cone, you report that PCE value as the value of your unknown sample. Sometimes the test cone softens, like after one reference cone goes down and before the next one, so it's between two standard cones. So then you report the PCE value midway between those two cones. And the deformation endpoint where the cone tip bends completely over and touches this cone plaque is the deformation endpoint. So you watch the cone bend down until it touches, and then you compare it to the reference cones. So here's a table of tabulated cone numbers. Goes down here, then up here from 12 to 42. And their endpoints where they deform and touch basically the cone plaque. So this PCE value really sets the upper limit, the upper use limit for these materials. You can't use it beyond these temperatures, and you don't really want to use it close to these temperatures because it's already deforming. So you go 100 or 200 degrees F lower than these points, and you're probably safe using that material. This is a little video of how these materials behave. These are 3 cones that are self-supporting, so they have a triangular shaped base. And so this is the time versus temperature. And as you're heating them up, you can see the cones are starting to deform. So this is a lower temperature one. This would be a higher temperature one, and this one would be one in between. So then you measure the angle of deflection. And since it's on a self-supporting stand here, the endpoint would be right there where it was 0 degrees. So this one has an endpoint. Well, it's gone now, but it was shown in, I think, 1,020 degrees C. So that's how the cones bend. The cone plaque is sitting in a furnace and it's rotating to provide a more uniform temperature distribution. And visually, someone is observing the cones and watching them deform. And then you make your estimation of what cone value it was. So a final report would look something like this. And I removed the customers and the sample IDs from all of these, so there are a lot of blanks, but you got a PCE value. This one was 20 to 21, and that corresponded to that deformation range, 2847 to 2883. So this cone bent, the sample cone bent between these two standard cones, 20 and 21. And this one, the PCE value of 17 bent at the same time as cone 17 did, and that's 27, 54 degrees F. So that's the PCE test, and it's used a lot to rank these fire clay refractories. And again, this is where it's deforming quite significantly, and it's basically melting. You can't use material up to its PCE value. The last part here is a C288 ASTM test, and the fire clay refractories and Super Duty and high aluminum refractories are used a great deal in a blast furnace, and it's a large structure, almost 200 feet tall, maybe 40 feet in diameter. The sidewalls of a blast furnace are lined with aluminum silica refractories. And we'll go over how a blast furnace works and how it's zoned and how it's lined later. But in a blast furnace, you're generating a great deal of carbon monoxide. So carbon monoxide can attack these refractories and actually disintegrate them. If you have free FeO in your aluminum silica refractory, it's a catalyst or a nucleation site for this reaction. The CO in the gas phase combines with carbon. The furnace has coke in it, so there's a great deal of carbon, and that forms CO2. So the carbon forms on this catalyst site in the material. So the carbon forms and builds up and keeps building up and growing until it disintegrates the refractory. It just forms and causes a great deal of pressure and disintegrates the refractory. So carbon deposits form on iron nucleation sites in the fire clay or even high aluminum refractories. This carbon deposit just keeps growing until it disrupts the entire structure. It'll first crack and then it'll disintegrate. So obviously you want to make sure you have an aluminum silica refractory that doesn't degrade in carbon monoxide for that application. So the test provides an accelerated exposure to high concentrations of CO gas, and it determines the potential material behavior in a very short time. So the results obtained in this method are used to select refractories that are resistant to CO disintegration. And there are other applications besides blast furnace that have carbon monoxide as one of their byproducts. This test asks for 10 samples. They're 9 by 2.5 by 2.5 bars or 9 by 3 by 3 inch bars. They're basically a half of a 9-inch straight that's cut in half along the length. If you're testing a castable, you may use a fire clay castable in this type of application. We didn't talk about castables yet, but you can bond fire clay aggregate with calcium aluminate cement and make a castable. If the samples are unfired, you need to fire them for 5 hours at one of these two temperatures. 1,000 degrees F removes the water that's physically and chemically held in a castable. And if you fire it to a higher temperature, you also remove the water, but you may be tying up some of the iron compounds, maybe in the glassy phase, and you might actually, that will inhibit carbon deposition. So you need some type of heated chamber. It has to be gas tight, and the test is not run at a high temperature, so you use a stainless steel shell. Typical dimensions would be about 18 inches in diameter and 36 inches tall. So you can put in quite a few samples in this volume. It's heated by resistance elements on the outside of the shell. You need a thermocouple well to measure the interior temperature and a gas inlet and a gas outlet as you pass the CO gas into the furnace and it exits. This is a dangerous test, so you have to isolate the equipment. We have a CO disintegration furnace in its own building, by itself, isolated, not attached to anything. It's well ventilated and it has CO detectors that as soon as there's a leak or an increase in the CO content, it shuts the whole system down. So you got to be real careful with CO. That's very obvious. So the samples are placed in this chamber. They're heated only to about 940 degrees F or about 500 degrees C. And you heat them up in a nitrogen atmosphere. And then when you reach the test temperature, 940 degrees C, you switch over to a CO atmosphere. And that gas has to have at least 95% carbon monoxide. And you have to flow the CO at a rate of at least 2 cubic inches per hour per cubic inch of sample volume. So it has a minimum flow rate. And you run the test for 100 or 200 hours. 100 hours is usually a significant amount of time. And if you're going to have CO disintegration, it's going to happen by the time you reach 100 hours. Some other industries, the steel industry they have some variations on this where they run 40 or 50 hours. Some people like to run 200 hours. But if you run 100 hours, you'll see what's going to happen. So after your time period, you shut the CO flow off and you cool it down in nitrogen. So you can classify the results, the disintegration as follows. It's a visual test. A lot of ASTM tests have no numbers for outputs. They're visual. We looked at the alkali vapor test is primarily a visual test. So if nothing happens during the 100 hours or 200 hours, however long you test, if no carbon deposits build up and no material is popped off or there's no cracks, it's rated unaffected. If you develop pockets of carbon, deposits of carbon, you may develop some surface pop-outs. So that's called effective. So the destructive action is confined to just surface pop-outs, and they're usually a ½ inch or less in diameter. So you'll see little pieces of the refractory popping off, and underneath that little piece that pops off, you'll see a black carbon deposit. So there's another, this is affected surface pop-outs. This is affected cracked. So if the destructive action produces pop-outs that are much bigger in size, bigger than a ½ inch, or it starts cracking the material, or both things happen, pop-outs and cracks, it's affected cracked. And then if all of this occurs and it's quite severe, it's called destructive. And you can simply take hand pressure and the sample falls apart, breaks into pieces, if it hasn't already disintegrated into basically a pile of powder. So this is what a test looks like, a test report. Again, I delete what's up there, so all I know is a refractory. I don't know what type. But this one was pre-fired at 1,000. So it was probably a castable. The test temperature was 930 and the test time was 100. And there are 4 different samples here. None of these samples did very well. They're all effective, cracked, or destructive. So that's the way they were rated. None of them in this particular test did very well. So here's a photograph of 3 samples. And this is the before photograph. This is the after photograph. So this is before testing. This is after 100 hours of testing. And in this particular test, these would be rated unaffected because nothing has really happened here. They look the same before and after the test. They have a little dark carbon deposits on the surface, but that's all. This particular material, this is before the test. And this is after the test, after 100 hours. And you can see these materials did rather poorly. These got to be rated complete destruction. You can see some of the carbon deposits, these black spots. Most of the carbon deposits are in the interior and they're causing these materials to crack and fall apart. This is the kind of condition where if you just with hand pressure, these would fall apart. So that's complete destruction. So I think that's the last slide. So that finishes up the alumina silica refractories and a couple extra ASTM tests that are relevant to these materials. Anybody have any questions on this?